Yeah, so we have we went over this graph right here, right? Which basically, again, just to recap, right? Skin effect happens when you apply frequency higher than DC, right? So any frequency other than DC will introduce a skin effect, right? And the physical implication of that is that the wire will have increased resistance due to this skin effect, right? And so the suggestions was that if you are selecting the wire size for given frequency, you want to make sure that the radius of the wire, right, at that frequency, operating frequency, the radius of the wire that you choose should be less than the skin depth, right? Because if that's the case, then you're practically covering the entire cross-sectional area of the wire, right? So if let's say that per given frequency, per given operating frequency, let's say that the skin depth, let's say, is this much. Let's just say, right, from there to there. Let's just say that's the skin depth. Then when you select it, when you select the wire, make sure that the radius or the skin depth, let's just use the skin depth as our reference. The skin depth should be larger than the radius of the wire, right? So if I assume that the wire is just round or circle, cross-sectional area is a circle, right? And here's the radius, right, of the wire, then that's about the same, right? And so ideally, theoretically, if they are the same, then you're practically covering the entire surface, right? But to ensure that that you are covering the entire cross-sectional area of the wire, right? You want the radius to be smaller than the skin depth, right? So something like, let's see if I can draw that. Something like this, maybe, right? So a smaller wire, basically, right? Because the skin depth is about this much, right? That's the skin depth. And there's the radius of the wire, right? So if the skin depth all around the wire is that much, then you can see that, you know, the entire cross-sectional area of the wire will be used, okay, for sure. So that was the conclusion that we had from last lecture, right? By looking at the skin depth, we can use it to select or choose the size of the wire used for the inductor or transformer. Okay, so that was last time. And then here's a table that shows recommended wire gauge for a range of operating frequency, right? It's a good table to use as a reference, right? Of course, you don't have to follow this, right? There might be some refinement in the design where, you know, this may not apply at all, but at least this should give you a good starting point, right? In terms of selecting wire size per given frequency. This is only strictly with respect to skin effect. So if the skin effect is the most dominant factor, then this is probably a good, this I would say would be a good table to refer to. But there are other things, not just skin effect. We're going to learn another factor in increasing resistance of wire, right? So based on skin effect only, you can see that, for example, if let's say DC to DC converters typically between, I would say, 200 kilohertz to 350 kilohertz, that kind of range, right? Ideally, you might want to use wire, gauge 42, right? Ideally, but again, this is just one consideration, right? This is a good starting point for you to when you select the wire size for the magnetic components that you use for this frequency, range of frequency. Any questions on this? All right. Let's see. Now, this is just another graph to show you. This is copper. How skin depth, varies with frequency. And as we already know, as the frequency is higher, the skin depth is getting smaller and smaller, right? Meaning the electrons going to be pushed more and more toward the surface, right? So this graph makes sense to me. Okay. Yeah, let's talk about the other effect. Right? In addition to skin effect, we also have this proximity effect. I think this is something that's new for you all, right, to learn. I think everybody's familiar with skin effect from electromagnetic class, maybe 335, right? But there's another effect that's impacting the resistance of a wire. That's called proximity effect. Right? Skin effect, right? That is due to its own current, right? So if this is a conductor, this conductor has current, right? And skin effect is basically the impact that we get from its own current, from the conductor's own current, right? So because of this current, you're gonna have skin effect in this wire, right? But proximity effect is slightly different. It is both are coming from eddy current, right? From eddy current. Eddy current that is due to the magnetic flux around the wire. But proximity effect is not really due to a conductor's own current, but rather is due to current from the neighboring wire. So, for example, if I have two conductors right here, right? And each wire will have skin effect, right? So each wire will definitely will have skin depth. But again, skin effect is due to its own current. But what about, for example, if I call this wire, the plus wire and the minus wire, right? The plus wire, right? If you do the right-hand rule, right? If the current goes in, plus means in, I believe, goes into the page, then the magnetic flux, right, due to the plus conductor is going to be clockwise this way. Yes, it's going to be clockwise. You agree with that? Clockwise, just like that, right? Okay, and then that's fine. And then if you look at the minus or the negative conductor, right, current is leaving, right? Go ahead and do right-hand rule. What do we get here? Right-hand rule, if it's out, that's going to be counterclockwise, right? So it's going to go this direction right there. You see that? So right there. Okay, so because of this, you see that if you look at the space in between the two conductors, right here, take a look at this space between the two conductors and take a look at the direction of the fluxes, right, caused by each conductor or both conductors. You can see that both fluxes are pointing down, right? They're the same direction. The magnetic flux, they're not canceling in between the conductors, that they're adding up, right? So that means we have a strong magnetic field between these two conductors, right? If there's a strong magnetic field between these two conductors, then the electrons will be attracted toward that toward the space between the two conductors, right? So you can see that in the electrons will be attracted toward that side of the middle, the space in between the two conductors, right? If you look at the plus conductor, then the electrons will be pushed toward the right side of the conductor, whereas if you look at the negative conductor, then the electrons being pushed to the left side of the conductor. right? So now the electrons are concentrated that way, right? In the shaded areas right there. So that's where the electrons will be concentrated more than the rest of the cross-sectional area. So I'm going to erase this, right? So this effect where the electrons within a conductor is being affected by magnetic field produced by the other conductor due to the current through the other conductor, then we call that effect proximity effect, right there. Is that clear, or does that make sense to you? Now you know the difference between skin effect and proximity effect, right? I think I have another example. Yeah, right there. So let's say I have 3 conductors, right? Now all of them have currents into the same direction, right? So in this case, going into, right, the page. So into the page means what now? Clockwise, right? Yes, clockwise. Clockwise, that way. For the first one, right, I'm gonna put the arrow in between the 2 conductors, and let's do the second one between the second conductor right here, clockwise again, right? Clockwise again, like that. And actually this is pointing that way, is pointing that way, right? And then on the bottom side is pointing this way and this way. And then lastly, the third conductor, clockwise as well. Just like that. And in the middle, I forgot to, right there. Okay, and this way as well. Okay, so what do we see here, right? We see a magnetic field between conductors, between 2 conductors are canceling each other, right? So there's practically no magnetic field between 2 conductors, none here, right? There's none here either. You agree with that, right? So no magnetic fields between 2 conductors. However, if you look at the magnetic field above 3 conductors, each conductor, right? Left to right, left to right, and left to right, right? So we can see we have a strong magnetic field that is pointing to the same direction, right? That way. And then if you look at below the conductors, you can see that all 3 magnetic fields, right, due to the 3 conductors, these are all pointing to the left, right? Same direction. So we have a strong magnetic field above the conductors, and strong magnetic field also below the conductors, right? So imagine that, right? Imagine we have strong magnetic field above the conductors. That means electrons will be pushed to the top of, right, of the cross-sectional area of the conductor. At the same time, some of the other half of the electrons, roughly, right, the other half of the electrons are also pulled toward the bottom side of the cross-sectional area of the conductor, right, due to the strong magnetic field below the 3 conductors. Okay. So then, because of that, you can see the concentrations of the electrons in this case, or in this example, is different from what we have earlier, right? Earlier, they are concentrated toward the center of the 2, or the space between the 2 conductors, but here they are concentrated both to on the top of, around the top of cross-sectional area, or bottom side of the cross-sectional area, just like that. Okay, let me erase that. Any question on this? And you can see that in between the 2 conductors, since there is no magnetic field, you can see no electrons are, attracted to this area right here, right? Nothing there. It's nothing there, right? Nothing there. Any questions on this? All right. So that's, again, proximity effect, right? This happens due to the interactions between the conductors, right? Okay. Now, if there's only one single conductor, this is not going to happen, right? If I just have one conductor, not three, just one, then it's going to be just purely skin effect, right? It's just going to be depending on a skin depth, basically, right? Which is toward the surface of the wire all around, right? With the depth of skin depth, right? So that's what happens if you just have one. But as soon as you have more than one, multiple conductors, right? Then you're going to see proximity effect as well. So that's something I believe is new for you to learn here, is that in addition to skin effect, you also need to worry about proximity effect. That's why the entire, the whole thing about magnetic design is quite complex, because now you learn something new here, is that not only that you have to worry about, skin effect now, as soon as you put in more wires, you have to worry about proximity effect, right? And notice that, this is a common configuration, right? And this could be this configuration right here, this example, right, where you have three conductors, sitting next to one another, right? This could be, formed by windings, right? If I have magnetic core, right, and I wind three turns right there, just like that, right? And then if you look at the surface of the core, then it looks exactly like this, right? That's exactly like that, right? All three will have the same current into the same direction, right? And so you're gonna have proximity effect if you are making an inductor, okay, with multiple turns. Right now, this is still a simpler case, right? What happens if you have multiple layers, right? You have more conductors here, right? More conductors. So now things get more complicated, right? When you have multiple layers. It's already complex with one layer. Now, if you add more layers, then you can see the effect of both skin effect and proximity effect becomes just complex. In a transformer or inductor, the inner windings operate in a field created by the outer windings. Yeah, so that's an example of how multiple layers would operate, right? Inner winding means, this winding, for example, right? I'm just gonna redraw. Let's say this is the core, right? And then you're putting first layer, sorry, second layers right there, right? And you can see that the top layer will definitely affect the bottom layer, right? And vice versa, right? So they're both interacting in terms of proximity effect. Right? So same thing if I add more layers, right? More proximity effect, right? From more currents, okay? As a general rule of thumb, the wire diameter or the layer thickness is usually less than twice the skin depth at the operating frequency. Less than twice the skin depth. So less than twice the skin depth. So if let's say you have the first layer right here of the inductor, right? And according to this general rule of thumb, the thickness of this layer should be what now? Should be less than twice the skin depth, right? So that means what? What does it tell us about wire size? That means the diameter of the wire, right, should be less than twice the skin depth, right? So right here, again, if I have multiple windings just like this, right, then based on this general rule of thumb, the radius of this wire, right, should be less than, let's call it D. Right? D should be less than, what is it, twice the skin depth. Okay, so that's the implication of that general rule of thumb right there. So anybody disagrees with that? As a general rule of thumb, the wire diameter or layer thickness is usually less than twice the skin depth of the operating frequency. So that gives us kind of a clue on, or starting point on, how to size the wire. Okay. Any question on this?
Does that mean with higher frequencies, like, you know how you mentioned that higher frequencies we have like smaller skin depth, right?
Mm-hmm.
Because we can't really physically change our wires, does that mean that we have like physical limitations too?
Well, you choose you choose the wire after you know what the operating frequency is, right? So one of the parameters typically when you're designing an inductor is you will ask, okay, what is the operating frequency of the inductor, right? And then based on that, you can determine the size of the wire, right? If it's multiple layers, then that's the rule of thumb right there, right? If it's only a single conductor, you know, not forming any inductor or transformer, then you can follow the skin effect table when it comes to wire sizing, like this one right there.
Okay, yeah, perfect. Thank you.
Okay. All right. So then the next question is there any, a better or more precise way of looking at this more comprehensively? In terms of yeah, having general rule of thumb is nice, right? But it'll be nicer to be able to have a more refined or more defined, there you go, a more defined guideline for us to select wire size if we are going to design inductors or transformer with multiple layers, right? I mean, this is all good, right? I'm not saying this is bad. This general rule of thumb, I mean, that's still good. But if you want to have a more defined or more quantitative guidelines, right, for a different number of layers, for example, then we do have the tool to do that, right? So that's what's next, right? So instead of using this general rule of thumb, I'm having a hard time speaking today. Sorry about that. General rule of thumb, then we could use this next tool, right? Now, this next tool takes a look at resistance or wire resistance from all of the effects, not just skin effect. Now we know proximity effect. It also looks at the DC effect, right? So DC resistance, skin effect resistance, and proximity effect resistance, right? So in general, wire resistance consists of these three resistances, okay? Our DC, our skin, and our proximity, right? And the whole thing is called RAC, right? The AC resistance of the wire. So RAC is equal to RDC plus R skin plus R proximity. And this is related to today's experiment too. In the video, I didn't actually think about it until I made the measurement, and you'll see that in the video as well. When I tested the inductor with and without the core, right? You see that I was asking myself in the video, and I didn't delete it because I think it's important information for you. Because I didn't realize it until until I looked at the two different values. The meter that I'm referring to is an LCR meter. This is the meter that we have in the lab that we can used to measure inductance, right? And not only that it measures inductance, it also measures resistance, right? Now, when it comes to resistance, this meter can also measure AC resistance and DC resistance, okay? So for the lab, I think what you need to calculate is DC resistance of the wire. So just the DC resistance of the wire, right? Because that's typically how people actually measure, right? How do you measure? What would you do if you are in the lab right now, right? What would you do to measure resistance of a wire? Typically, what would you do? Can you tell me? Anybody?
Just place an ohmmeter across it.
Exactly. Yes. Just use the ohmmeter, right? And then you would put an ohmmeter across this wire, and then you get this resistance, right? But guess what? You know that ohmmeter, right? It's actually only measuring DC, right? It's only measuring DC, and that's what people typically, do when they measure wire resistance. They typically measure DC resistance because they just use a simple ohm meter, right? But what's nice about this LCR meter that we have in the lab is that it can measure RAC as well, which depends on frequency. And you'll see that in the lab. You'll see that in the video, that RDC stays the same, but RAC changes as I put the magnetic material inside the tube. You'll see that, right? So that's an interesting observation that I made, that I have in the video. You'll see that as well. Okay. So anyhow, again, in general, wire resistance consists of 3 different components: RBC, R skin, and R proximity. And then if you divide both sides by RDC, then you get this variable called, or parameter called FR, right? So FR, which is the ratio of AC over DC. So again, just divide both side of the equations with RDC. Then you have this equation, right? Right there. And the ratio of AC to DC only is called FR, right? Yeah, the FR variable, right? And this is a function that that this tool that we have next will be we will look at. So it can be shown that since all of those are a function of frequency, except for the DC resistance, then it can be shown that I actually have the paper that shows the derivations. It was very long derivations. You can also find this, or you can Google this. This equation is called Dowell's. Did I have it right here somewhere? No. I don't know how to say the word here. What is that name? I thought there's a name here. Interesting. Oh, right here. Dowell's equation, right? So that's the person who found this approach, this method. So it can be proven from that derivation that FR is going to be a function of X and M. That's equal to all of these equations right there, the right-hand side of the equation, where A is equal to this equation right there, and B is equal to the next equation right there, okay? And X, remember that FR, what is FR again? That's the ratio, right? Ratio of RAC to RDC, right? It's a function of X and M. What is X, what is M? X is layer thickness in skin depths, and M is the total number of layers in the winding section. It has to be integer, right? So this is a useful tool, useful equation for us to use if you are designing an inductor or transformer that has multiple number of turns as well as multiple number of layers, right? So you can just plug in X and M depending on how many layers you have for the magnetic component that you're designing, and you can assign different layer thickness with respect to skin depths. Of course, this is something that you would know for the per given operating frequency, right? So you must know the switching frequency first. Once you know this switching frequency, then you can find the skin depths, right? And then based on that skin depth, you can vary the value of X, right? Based on how much is the thickness with respect to the skin depth, right? So that's what X is. Any questions so far? So on the next page, we're going to see two examples, two graphs that shows how we can apply these equations, okay? And in these graphs, we have three different plots, right? One that shows the sum, the other one that shows the RDC, the proximity resistance, and the resistance due to the skin effect, right? So the sum is by itself is equal to RAC, basically, right? So keep in mind that sum is equal to RAC. So you're gonna see four plots right there. So here's an example, and you can see from this first example, the x-axis is X. What is X again? That's layer thickness, right? In terms of skin depth. Double check first. Layer thickness in skin depths. So that's X. So what does 1 mean then? When X is equal to 1, it means what? It means that the layer thickness is equal to 1 times skin depth, right? So maybe I should write that down, huh? When X is equal to 1, it means that layer thickness is equal to 1 times the skin depth, right? And if it's 10, then it's going to be 10 times skin depth, and so on and so forth, okay? Is that clear of what X means? Right? So again, that's layer thickness, right? So again, if you have inductors with multiple layers, then that will be the thickness of each layer. And then on the y-axis, we have relative contribution to RAC. And there are 4 different plots there, right? The first one is the sum. Let me use red so you can see. Right, sum, and then RDC, the DC resistance basically, and then the resistance due to proximity, and the resistance due to skin effect, right? So this is very useful, right? It's a very useful tool to have, and in the future, if you ever design multiple layers, right, of inductors and transformers, this is something that you might want to go back and refer to, okay? Because it tells you what will be the recommended thickness of the layer by looking at this graph, right? So here, we are assuming that M is equal to 1. So just one layer, right? Just one layer. And then what we are looking for, right, to minimize loss is what? Anybody? What will be the point of interest for us from these graphs? Remember, these are all resistances, right? If you are designing this and you want to make use of this graph, where do you think is the point of interest from this graph?
The sum?
The lowest.
That's correct. The lowest of the sum, right, of all. In this example, is this point right there, right? That's the lowest. Right? It starts from high, right? Basically, it is the same as RDC. So you can see that as you are increasing the layer thickness, right, with respect to the skin depth, right, start from low, for example, the RDC dominates, right? But then as you are increasing it, you can see that that now proximity takes into effect, right? Proximity takes into effect, and then finally at the end, skin effect takes also affects the entire sum. But for us, right, in terms of minimizing the loss, what really is interesting is that we want to get that point right there, right? Because that's the point where we have the lowest amount of resistance, right? RAC, the sum of all three, right? So our interest would be the sum of all three resistances, not just individual one, but the sum of all three, right? If we want to minimize the loss. Okay. Now it might be that the priority is different for different design. Maybe you want to, for a different application, maybe you want the least skin effect instead of the entire resistance. So minimizing the loss is not that important, but minimizing skin effect is important. Well, in that case, for this graph right here, that would be the point, right? Of course, this graph goes all the way down if you extend more, right? But just based on this graph, for example, right? You can see that right there is the lowest. But if you want to go from 0.1 to 10, unfortunately, this doesn't cover the entire graph. You're gonna have to extend this, right? And it's gonna be linear. You have to extend it. So you have to graph it yourself, basically, until you get the point of which one is gonna be the more practical layer thickness that you choose, right? Okay. Yeah, so that's that. And then for the next example, the number of layers, there's 5 of them right there, right? And then the same thing, right? You can see that we have 4 different plots, right, representing 4 different resistances. And our interest for minimizing losses would be the sum, right? Sum of all 3. And we need to look for the minimum point, which is it right there around? Looks like, right? So around here, that will be the thickness that you should choose, the thickness of the layer, of each layer that you should choose in terms of the skin depth, right? In order to minimize loss. I forgot, let's go back here. For this one, the minimum is about that point right there, right? So I need to mark it, there you go. All right, it's not really a straight line, but it's around that area. And that's about what? That's a log scale. 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's about maybe 1.5-ish, right? I don't know, 1.5, approximately 1.5 skin depth, right? So it looks like for m equals to 1, so if you only have one, if the inductor only has 1 layer, see, it looks like from this graph, right? The thickness of the layer should be 1.5 times the skin depth, right? In order to minimize the loss. Does that make sense from this graph? So that's why this is very useful, right? I like this graph because then, you can just, read the graph and figure out which would be the minimum total resistance to give us the minimum loss. Okay, you agree with that? Right. For the next example, it's a different point, right? You can see the point shifted to the left. You increase the number of layers, you can see that the minimum point is shifted to the left. And here, this has about what? 2, 3, 4, 5, 6. That's about 0.6 of the skin depth. So when you have when the inductor has 5 layers, right? For a given frequency, right? That you already know, that this skin depth, or not skin depth, the thickness of the layer should be around 0.6 of the skin depth to make it or to minimize the amount of loss due to resistance, right? So that's to me, it's very useful tool to know, right? So rather than having rule of thumb, now we can use these equations, right, to determine what layer thickness is required, or what layer thickness should we choose in order to minimize loss, right? So I think this is a better method than just the rule of thumb, right? Okay. So any questions? Is that clear of what the purpose of this equation is and how to use it, right? So if you want a different number of layers, you can go ahead and plot it yourself, right? Different number of layers, that's M, and then X would be your variable, independent variable, right? A function of skin depth, basically. Okay. Any questions on this?
Yeah. What is the units of X in this case, the skin depth? Or
I
thickness?
don't think there's any unit. Oh, I'm sorry, there is a unit. The unit of skin depth. What is the unit of skin depth? Length, right? Dimension of length. It could be millimeters. It could be, if it's SI, that's going to be meters, right? But I think usually people use millimeters. What is the example we used previously for skin depth? Could be inches too. So it's a unit of length.
And because we had resistance, right? Would we use the unit of ohms for those, like the RDC and R proximity? Because those are functions.
No, X by itself is the layer thickness, right? So that should be in length, unit of length.
Correct. Yeah. And then for the y-axis, we had like relative to RAC, right, which is the sum of all of them.
Oh,
so
yes.
Would we have ohms for that?
That's correct. Yes.
Okay. Awesome.
The y-axis is ohms because it's resistances. That's correct.
Yeah. Perfect. Thank you.
Okay. So it looks like for this example, I use centimeters, right, for skin depth. Okay. Any other questions?
Yeah, I'm a little confused about what X is, because on the X scale, you just have like numbers, but then you multiply it by the skin depth. So is X like unitless, and then there's like layer thickness equals X times skin depth?
Yeah, so X is layer thickness. So let's say I have one layer, right? For the first example, let's go to the first example. Yeah, right there. So let's say that this is the surface of the core, right? So this is the cross-sectional area of the conductors, right? So X is the layer thickness right there from here to here, which is basically close to the diameter of the wire, right? Do you agree with that?
Yeah.
That's X right there.
So would you use X, like if say we were to plug in X in the equation, would it be like a constant, or would it be like a constant times skin depth?
A constant times in depth.
Okay.
So that's something that you vary, because that's the independent variable, right? So you would vary X. Yeah, you vary X from point, in this case for this graph, you vary X from 0.1 times skin depth to 10 times skin depth.
Okay, cool. Thank you.
Is that clear now, or still confusing?
No, that makes sense. I wanted to make sure, like, if I were to plug in X, I'm plugging in the right thing.
Okay. Yes. So if it's only one layer, then that layer thickness X would be around what is it again? 1.5. Is it 1.5 really? Maybe I messed up on that one. This is 1. This is 2, right? 2, 3. Yeah, I think it's about 1.5 roughly. So about 1.5 skin depth. Right? If it's only one layer. For this next example, there, how many layers is this? That's 5. Oh, okay. I don't know if I can draw that, but yeah, you can, picture, you have 5 layers, right? Something like that. Maybe next time I just draw it beforehand, or I'll put it in the notes so it'll be clear. So again, X is going to be the thickness of each layer, not the entire 5 layers, but each, right? So from here to here, that's X. So in this case, each layer should be around 0.6 of the skin depth, right? Okay, and it looks like I have another one right here. Number of layers 20. So for 20, again, it's shifted more to the left, looks like, right? That's the trend. So that's the minimum, looks like, is at this line right there, right? That X value. What is that? 0.3. So that's 0.3 skin depth. Okay. Yeah, let me know if it's still confusing to you, but hopefully now you understand the importance of this equation, and by graphing them, you can clearly see where the minimum occurs, right? That's what should be in most cases, the point of interest to minimize loss.
Well, thank you.
Yeah, okay, you're welcome. All right, I'm just gonna skip that one. That's just a way of relating proximity and skin effect. So we're done with this chapter, finally. All right. And then chapter 2 is also a review, but it should be a quicker, right? Especially, I believe you did this in 255, didn't you? Right, magnetic circuits. So I'm going to go through this rather quickly, and so we can start, this covering the inductor design and transformer design chapters. All right. So bear with me on this one. Magnetic circuits. Then we already know permeability, right? That's mu. It is the ability of a material to conduct flux. Mathematically, it is the ratio of the flux density B to the magnetic field intensity H. So mu is equal to B over H, right? Absolute permeability, mu naught, is the permeability in a vacuum. So we learned it from previous chapter. In CGS system, mu naught is equal to 1. Unit is Gauss per Oersted. I believe that's how you say it. And then that's equal to 1 times 10 to the 4 Tesla over Oersted. Right? In MKS, mu naught is equal to 4 pi 10 to the minus 7 Henry per meter. Right? So gotta watch out for which system is being used. If you look at, I think I mentioned this last time, when you're looking at data sheet for magnetic materials, people just mix this up, okay? Sometimes in one data sheet, they mix up both, which is the most terrible that they've done, on one graph, they use CGS, and another graph, they use MKS. That's just terrible. But hopefully we don't see too many of those anymore. All right, in the BH or magnetization curve, the slope at any given point gives the permeability at that point. Okay, permeability is not constant, right? It depends on the magnetic field strength H, right, which is the operating conditions, and then applied frequency, temperature, and material use, right? So that's what mu would depend on, right? Depend on magnetic field strength, applied frequency, temperature, and materials use. And these are just typical relative permeability of several magnetic materials. I won't go through those. I don't know, that's pretty high. Look at that, 20,000. All right. Here's the picture to show to show you that we have a BH curve right there, right? That's what you're familiar with. And then the slope, right? Don't forget that B is equal to mu H. So if you plot B against H, then mu must be the slope, right? So the slope of the BH curve, that corresponds to the permeability, right? So this curve right here, this one right there, right? That shows the permeability, right? And you can see that at the beginning, right, we have basically no slope, right? So zero slope, and then the slope start to increase, right? And then it is linear, right? Linear slope. So you can see that the slope now becomes constant, and then around this area is constant slope. And or sorry, not constant slope. Around this area, it gives you the maximum, right? The maximum slope, and then the slope gets smaller and smaller and smaller and smaller until it goes to zero again. So this curve right here shows that as you are traversing through this BH curve, the permeability or the mu or the slope, right? Gradually, not gradually, but start from zero, it goes up, reaches its maximum value, and then it comes down again, right? Okay. Okay, so that's a BH curve. Again, the point there is that don't forget that mu is the slope of our BH curve. Reluctance. The flux produced in a given material depends on the material's resistance to flux. Right? This resistance is called reluctance. Right? Reluctance of a core depends on the type of the material and physical dimension. Right? So only depends on those two. Okay, the type of the material and physical dimension of the core. Okay. Reluctance concept is similar to electrical resistance. Oh, before I go there, later on you'll see the equation for this. Okay, so this is the conceptual, right? Conceptual. What do you call it? Yeah, the concept behind reluctance is that theoretically speaking, it should be so only depend on the type of material and physical dimension. But later you'll see the equation for reluctance. Or you already saw that in 255. You're gonna see that again here. Reluctance concept is similar to electrical resistance. The greater the reluctance, the higher magnetomotive force required to obtain a given magnetic field. Magnetomotive force. Magnetomotive force required. I'm just going to say MMF. That's too long for me. The greater the reluctance, the higher MMF required to obtain a given magnetic field. The relationship between MMF, flux, and magnetic reluctance is analogous to the relation between a voltage source, current, and resistance, which is convenient, right? Because we're EEs, we are very familiar with voltage, current, and resistance, but not so with MMF, flux, and magnetic reluctance. So it's good to be able to model magnetic circuits with electrical circuits, right? If we have electric circuits, by Ohm's law, you know that voltage is equal to I times R. And by analogy, in magnetic circuits, voltage is MMF, right? Current is flux, and resistance is reluctance. Right, so therefore, MMF is equal to flux times reluctance in magnetic circuit. Again, it's convenient to be able to use electric circuits to model magnetic circuits. On the left, we have the magnetic circuit, circuit. On the right, we have the electric circuit, right? In electric circuit, we have voltage source connected to a resistance, and that would produce current. In magnetic circuit, we have MMF that is connected to reluctance, in this case core, then that would produce flux inside the core, right? So therefore, magnetic circuits, as I said earlier, could be analyzed through electric circuit analogy. which is again nice. Recall in electric circuit, right? If you have a battery, plus minus that way, connected to a resistor, then you can see that using Ohm's law, current is equal to voltage divided by R. Right? And V again is called electromotive, or I didn't call it before, but V is voltage, and it's also called the electromotive force. There you go. Assuming R is constant, right? Assuming this R is constant, right? How do you get more current? Right? How do you get more current if R is constant? Then you can increase the voltage, right? How do you increase the voltage? Well, you can put more batteries in series, for example, right? And you can get more current that way, right? So you increase the voltage. How do you reverse the direction of the current if you have electric circuit? Instead of from left to right, I want current to flow from right to left. That's simple, right? We just swap the battery, right? Just flip the battery, flip the battery so that the plus is over here, the minus over there. So then you can see current should flow the opposite direction, right? So switch polarity of V. That's what you do in electric circuit. But what if you have magnetic circuit, right? Right here, magnetic circuit, right? And here's the electric circuit analogy of magnetic circuit, right? That's your MMF right there, right? By using this letter fancy F, MMF is equal to N times I, and then you see flux, which represent or analogous to our current in the electric circuit, and reluctance, which is analogous to resistance, right? So if you look at this picture, it is not clear, right? How do you increase the flux inside the core if you just look at this diagram right there, or that picture right there? That's not really clear, right? But if you represent it as an electric circuit, like this one right there, now we know, right? Now we know how to increase flux, right? Because flux acts like current. How? Well, two ways in this case, right? If you have electric circuit, there's only one way, right? Again, this is assuming reluctance is constant, okay? In electric circuit earlier, we can increase the current by increasing voltage. But if you have magnetic circuit, right, it turns out that you can do one of the two things, right, to increase flux per given reluctance. Number one is to increase the number of turns, assuming current is constant, right? Same current for the same current. Or you do the opposite, right? You can have the same number of turns, but then you increase the current. Either way, it will increase the flux presence in the core, right? But again, the main point here is that as soon as you represent magnetic circuit with electric circuit, it becomes easier for us to be able to analyze the circuit, right? Just like we did earlier, right? How do you increase the flux? Increase the N or increase the I, right? How do you flip the direction of the flux, right? Now, this is something that may not be clear even after you use electric circuits. But what you can do though, what is clear from the electric circuit analogy is that in order for this flux to reverse direction per given reluctance, you have to flip the polarity, right? So polarity has to be this right there. Okay, you agree with that part? Right? So then what's not clear though is how do you flip the polarity, right? How do you flip the polarity? Maybe one thing that's kind of one thing that you can guess is that, oh, if I change the direction of I, so instead of Ni, right, I'm going to do N times minus I, right? So instead of N times I, N times minus I. Then it will flip, right? Because the sign now becomes, so this is equal to minus Ni. You agree? So that's something that you could get from here, right? Purely from the equation right there, right? So that's one way, is by reversing the current that is being injected to this winding right there, right? If you go back to this picture right there, right? Minus I means you inject the current the other way from the bottom portion of the winding. So now the current leaves from the top, right there. That's one way. What's another way? Which is not clear from here. I don't think you will know unless you actually go back to the magnetic circuit. What is the second way?
Change the direction of your windings.
Yes, changing the direction of the winding, right? By right-hand rule, right? You know that for if you look at the magnetic circuit on the left, right? The way we are winding the turn, but if you use right-hand rule, the flux goes clockwise, right? But imagine if I do the opposite direction of the winding, right? So instead of out in, right, this is out in, right? I'm looking at this one right here. So I wind it out first and then in. What if I do the opposite? I went in first and out, right? So then, of course, by right-hand rule, the flux is going to go the other way around. Okay, so that's one thing that that this will not tell you. This electric circuit will not tell you. You get it from the magnetic circuit, but still, you know, we still have some useful majority of the what do you call it? Majority of the analysis can be done using the electric circuit analogy of our magnetic circuit. Okay, so that's, again, I just want to stress the importance of representing magnetic circuit with electric circuit, right? The reason why we learn this and the reason why I want to review this, right? Okay, any questions on this? If not, what else do I have here? Finding flux in the rectangular core. So the equation for flux is equal to B times A. B is flux density. A is the area, cross-sectional area of the core, which is right there. Sorry for my bad drawing here. I tried to draw this myself. Maybe next time I'll just use Visio to do this. And then from here, B is equal to mu times H times A. Right? And then H from there is equal to Ni over L. That's our MMF right here, right? And then LC is the magnetic path length, right? LC, that's the effective length of the core. That's LC right there. And so if you go back to the first equation, flux is equal to B times A, mu HA. So that's going to be mu times H, which is Ni over L, times A right there. Okay. And remember that flux is analogous to current, right? So we know that Ni is our voltage, quote unquote, right? So that's our MMF right there, right? So therefore, if we use the analogy that oh my God, that I is, oh, come on, that I is analogous to flux, then I is equal to V over R, right? Right there. Then and we know that Ni is equal to V, right? So therefore, if you look at this equation right there, what is the equation again? Flux is equal to mu Ni A over LC, right? And then Ni is our V. So that means if I separate the two, Ni LC over mu A, right? Like that. Then this is our voltage, and this must be our reluctance, right? Because I know that I is equal to V over R for a magnetic circuit is equal to MMF over reluctance, right? Since I know that MMF is Ni, therefore the remaining terms must be our reluctance. So from this equation right here, again, I agree to this, I know that that remaining term in parentheses is our reluctance, and that's equal to LC over mu A. L subscript C over mu A. There you go. So now we have the equation for reluctance. That's how you know the equation for reluctance. That's how you derive it, right, from this simple example, right? So right there is our reluctance. Now, remember earlier, I mentioned that reluctance is a function of two things. What are those two things? Do you remember? And I said earlier that we're going to look at the equations, right? But theoretically speaking, like conceptually, reluctance, it makes sense that reluctance should be a function of only the geometrical structure of the core. Oh, I just gave you the answer. And what else besides the geometrical structure of the core?
And permeability, so type of material.
Type of material, yes, exactly. Ah, man, sorry, I just gave you the answer. So it makes sense, right? Because reluctance has to do with the core itself, right? Nothing else, right? Just the core by itself. So therefore, reluctance should be a function of the material used for that core and how that core is shaped, right? So L and A, right? That relates to the geometrical structure or the shape of the core, right? Whereas mu, that relates to the type of material of the core, right? So here's the proof mathematically right there, right? That using this derivation that we just did, that reluctance is equal to LC over mu A, right? So LC and A, those are, again, coming from the shape of the core, geometrical shape of the core, and then mu by itself is the property of materials inside the core, used in the core. Okay, any question on that one? All right. Oh, okay, now determining MMF. Right, this is going to be important when we're doing analysis of magnetic circuits. Right, you can use the right-hand rule to determine the polarity of MMF. Right. So, for example, going back to here, if the four fingers, except for the thumb, right, the other four fingers are curling, right, in the direction of the winding, then if you unfold your thumb, then that's going to be pointing to the positive polarity of the MMF. Okay, so that's pretty straightforward, right? So an example here would be, okay, look at this winding right there, right? Look at how the winding is being wound around this core, right? So by using the right-hand rule, right, I know that for this MMF, the positive, when you draw this into electric circuit analogy, like that, then this voltage source will have the positive side on the bottom side of the source right there, right? Because you can see the thumb is pointing downward. Okay, so therefore flux will flow counterclockwise because of that. All right. Any question on this? I'm going to skip that. All right, and then lumping reluctances in the core, right? So if you have a core that shapes like this, right? Each single side of the core will have their own reluctance, right? So remember, reluctance is a function of what now? Sorry, what is the equation for reluctance? L mu A, right? So the mu is going to be the same, right? Because that's the same core, right? The same core means the same mu, right? So if you look at every single side, there's four sides, right? And all four sides will have the same mu, but it is possible that each side will have different length and different cross-sectional area. So calculation of reluctance, right, will typically involve looking at the details on the length of the path or in this case, the side, and the cross-sectional area for that segment, right? For that segment of the core. Okay. So in this case, you have 4 different sides, and if you want to represent it with an electric circuit, then you're going to end up with 1 reluctance from that segment, 2 reluctance from that segment, 3 reluctances, and then 4th reluctance, right? So then you have 4 reluctances total, right? And you can lump them up into just 1 single reluctance, right? Oh, I have the calculation for that, but I'm not going to do it today. I'll do it next time.